Welcome to Mrs. Z's Chemistry. In this video, we will discuss covalent bonds. In a covalent bond, the atoms share electrons. The electrons are not transferred from one atom to another, but rather each atom shares an electron with the other atom. This is a bonding pair of electrons. The atoms are not charged particles like ionic compounds. Therefore, they are not very soluble in water and don't conduct electricity very well at all. One thing I'm going to point out here so we don't get confused about the words transferring versus sharing. When you were in preschool or kindergarten and told you had to share your toy, that meant you had to give the toy up to someone else and you didn't get the toy anymore. This is not the way atoms share electrons. Giving up your toy to another child is the same way atoms transfer electrons. One atom no longer has the electron while the other one gets to have the electron. When atoms share electrons, it's more like when you and another child are both playing with a toy together. You both have your hands on the toy and both getting to play with it. This is the way atoms share electrons. They both get to claim the electron as their own. On this graph, we have the internuclear distance on the x-axis. As you can see here, it is measured in picometers. This means how close the nuclei of two atoms are, and it's measured in picometers, which is a trillionth of a meter. The y-axis measures the amount of potential energy the atoms have. Starting on the right-hand side of this graph, the atoms are far apart and have roughly zero potential energy. As they move closer together, the nuclei become closer together and the potential energy starts to decrease until they reach the lowest part on this graph. This is the distance the atoms have between them in a bond when they are at the lowest amount of potential energy. You can think of it like atoms wanting to rest or relax with a low amount of energy in their bond. The bonds between atoms actually aren't rigid, but in fact the atoms oscillate back and forth a little bit. They push closer together, pull back apart. As the nuclei get closer together, the potential energy increases sharply, but then they move back apart a little and the potential energy drops back down to the resting point of the bond where the lowest amount of potential energy is. Energy must always be added in order to break a bond. Another way to put this is the atoms must absorb energy in order to break the bond that they have. This is an endothermic process like we learned in our thermochemistry chapter. Energy is always released when bonds are formed, and this is an exothermic process. Remember, atoms want to have the lowest amount of energy when they form their bond. So they're going to release energy and then form their bond at a low amount of energy. The amounts of energy are equal and opposite for forming or breaking the bonds. So let's start with this H2. That means you've got two hydrogen atoms that are bonded together. When that bond breaks apart, you have two separate individual hydrogen atoms. So we have a coefficient 2 and no subscript 2. This process requires 436 kilojoules of energy. Another way to put it is we need to input energy into these atoms. The atoms need to absorb energy in order to break their bond and separate from each other. On the flip side, for this one, I'll do this in a different color. We'll do this in purple. When you have two separate hydrogen atoms, and then they form a bond with each other so that we have a 2 coefficient and then a 2 subscript, that releases, because of this negative sign, that releases 436 kilojoules. So energy leaves the atom as the bonds are being formed. When atoms share the bonding electrons evenly, this is called a pure covalent bond. This happens when the atoms are the same type of atom. One atom doesn't have a higher ability to attract the electrons, so they share the electrons between them evenly. However, if you have two different atoms in a bond, most of the time, the bonding electrons between them will not be shared equally. One of the atoms usually has a higher ability to attract electrons to itself, causing the electron density to shift towards it. This causes that atom to have a partial negative charge and the other atom to have a partial positive charge. We call this type of bond a polar covalent bond. Here's an example. When chlorine and hydrogen form a bond, they each share one electron with the other, but chlorine has a higher ability to attract electrons, so the bonding pair of electrons spend more time around chlorine than hydrogen. This causes chlorine to have a partial negative charge and hydrogen to have a partial positive charge. We say that the electron density is greater around chlorine than hydrogen. This funky letter here is a lowercase delta, a Greek letter. We use it to mean partial. You can draw it by writing an S and then connecting that bottom tail of the S to the diagonal part of the S. We will write a partial negative by the chlorine and a partial positive by the hydrogen. This concept of sharing electrons unequally comes from electronegativity. This electronegativity is the tendency or ability of the atoms in a molecule to attract bonding electrons to itself. Electronegativity is expressed in a qualitative measurement called the Pauling electronegativity scale. The scale assigns the highest value to fluorine because fluorine is the most electronegative element. Highly electronegative atoms attract electrons more readily than lower electronegative atoms. When the covalent bonds are formed between atoms with different electronegativities, a polar covalent bond is formed and the electrons are more densely populated around the more electronegative atom. Here is a periodic table with the Pauling scale of electronegativity numbers. There's actually no units attached to these numbers. They are a relative scale. Fluorine is set as the highest number at 4.0, as it is the most electronegative element on the periodic table. Every other element has a lower number considering how much less electronegative it is relative to fluorine. As we move across a row on the periodic table, as we get closer to fluorine on any of these rows, the electronegativity increases. As we move up a periodic table, up a column on the periodic table, as we get closer to fluorine, the electronegativity also increases. The type of bond made between two atoms will fall on a spectrum between pure covalent. If we were to draw the spectrum like this, we've got pure covalent on one end, polar covalent in the middle, and ionic on the far other end. Where the type of bond falls on this spectrum depends on the electronegativity difference between the two atoms. If you compare the two atoms and their difference is negative or is 0.4 or less, then we call that a pure covalent bond. So this is roughly 0.4. I'll say less than or equal to 0.4. A polar covalent bond is where the difference is somewhere between 0.4 and 0.8. And 1.8. And if the difference is greater than 1.8, then that is ionic bond. Different chemistry textbooks and professors may disagree on exactly where these numbers fall. Some will say maybe this number instead of 0.4 should be 0.5, or some textbooks may say that this 1.8 number should maybe be 1.6 or 1.7, something along those lines, which is why we call this a spectrum. Looking at the periodic table of electronegativity numbers, let's compare the difference between each pair. So we're going to look between carbon and hydrogen. This line between them represents the bond between carbon and hydrogen. Carbon has a value of 2.5 and hydrogen 2.1. So that difference is 0.4. Sulfur has a value of 2.5 and hydrogen 2.1. It also has a difference of 0.4. Both of these would be considered to be pure covalent bonds. They share the electrons quite evenly between them. Carbon and nitrogen have a difference of 0.5. We consider this bond to be polar covalent. The electrons hang around nitrogen a little bit more. The difference between nitrogen and hydrogen, we have a 3.0 and a 2.1, so the difference between them is 0.9. Carbon and oxygen have a difference of 1.0. Oxygen and hydrogen have a difference of 1.4. So we can see that these bonds are written in, as we move down this list here, in increasing order of electronegativity differences. So they become more and more polar as we move down this list. All right, let's use the partial negative and partial positive, here's partial positive, partial negative symbols on each of the atoms. Because carbon is more electronegative, its number is greater. Let's look at that. Carbon is 2.5. And hydrogen is 2.1. Carbon has the higher number, therefore it is more electronegative, so it will have the partial negative symbol, and the hydrogen has the partial positive. This means that the electrons hang around carbon more than it does hydrogen. Even though this number is still very, very low of 0.4, there is still a slightly uneven difference of sharing between these two. Sulfur is also 2.5, so it is the partial negative atom, and hydrogen is the partial positive. Between carbon and nitrogen, nitrogen is the more electronegative element, and carbon is the less electronegative element. Between nitrogen and hydrogen, nitrogen is more electronegative, hydrogen less electronegative. Between carbon and oxygen, oxygen is more electronegative, carbon is less. And between oxygen and hydrogen, oxygen more electronegative, hydrogen less electronegative. There's the answers written, typed up. Polyatomic ions contain both ionic and covalent bonds. So let's look at this sulfate, SO4 2-. There are covalent bonds between sulfur and oxygen. This means that sulfur and oxygen share electrons between them. They are not going to transfer electrons between them, but altogether, all 5 of these elements, the 1 sulfur and the 4 oxygens, have gained 2 electrons, giving it a 2- charge. So altogether, as one unit, this polyatomic ion can make an ionic compound with a cation, typically a metal that has lost 2 electrons, like magnesium sulfate. Magnesium makes a 2+ charge, so it can make a ionic compound 1-to-1, 1 magnesium with 1 sulfate. When magnesium sulfate dissolves in water or reacts with other compounds, the magnesium will break apart away from the sulfate. But the S and the oxygens are not going to separate from each other. The SO4 will stay together when it dissolves, when this compound, magnesium sulfate, dissolves in water. This is why it's important to be very familiar with your polyatomic ions, such as sulfate, nitrate, hydroxide, and ammonium. To remember that these are not going to separate. They are covalently bonded together, but ionically they can make a bond with a cation, either something like potassium or calcium, or ammonium with a positive charge can make an ionic compound with another negatively charged element.